Welcome to the USC Geology 101 video on mineral identification techniques. Throughout both your mineral lab as well as the 3 rock labs that follow it, it will be imperative that you are able to identify minerals and tell them apart from one another. The techniques we're going to utilize rely upon the properties of individual minerals. We call these tests diagnostic tests, as they will help us narrow down what mineral it is. These tests fall into one of 2 categories. These are going to be destructive and non-destructive. We always want to start with non-destructive tests. These are tests that do not damage the sample. The first property people tend to look at is color. Now, geology is a very visual science, so if you are colorblind, please let your IA know, as we can help out with this. But the issue with color is it can be the exact same color from multiple different minerals. So for example, these 2 minerals are both gray, or one mineral can have many different colors. So for example, this is a sample of fluorite. This is also a sample of fluorite. This is a sample of fluorite. And this is a sample of fluorite. So I know these colors might look a little off to you based on how the white balance is working for this camera. This is currently yellow. This is purple. This is light green. This is a nice light blue. So all 4 of these samples are the exact same mineral. It just depends on what's giving them those colorations. So color tends to not be a super great tool to use. However, what's much more useful to us is being able to tell if something has a light color versus a dark color. That's going to be our bigger difference to begin with. Following color, we also want to know about whether or not a sample is transparent or if it is opaque. So a sample that is transparent will allow light through. So it's hard to see because this is a clear sample on top of a white background, but all light passes through this. You can actually see light passing through it in the shadow of it. Compare that to something like this sample. No light passes through this at all. This is an opaque sample. The other aspect that we want to start with as far as visual appearances go is luster. So what we've looked at so far, what color of light gets reflected from it? How does light penetrate through a sample? Luster is how it interacts with the surface of a sample. So we have 2 categories for this in our level. We have metallic. So these are going to be things that look like a metal. They're going to typically be opaque and shiny, but they look like a metal. The other option is going to be non-metallic. This comes in a lot of varieties. So you will notice that this does not look like a metal. That's always going to be your big hint for this, is it's not looking like a metal. But this one has kind of like a pearly vibe going on. This one has more of a glassy vibe. This one is very, very matte, so it doesn't have a high amount of reflectiveness. Similar to this one, it's not super glassy. Some of them are going to be dull, so they don't actually reflect a lot of light at all. It's just a very matte appearance. All of these fall under non-metallic lusters. This is going to be the vast majority of the samples we look at. The samples that tend to confuse students the most are going to be dark colored, opaque samples that are quite high gloss. So this is a sample of biotite mica. You can see that it has a high amount of reflectivity. It has a glassy luster. That falls into non-metallic. It does not look like a metal if you were to hold this. So those are most of our non-destructive methods. Another non-destructive method is looking at a mineral's cleavage. Now, if you want to go really in depth with cleavage, you are going to need to break a sample. So we are not going to do that in most of our environments for the 101 labs. Some of the samples you will get to damage, and that will allow you to see a fresh cleavage surface. But really what we want to figure out is how does a mineral break? So, for example, this mineral here breaks kind of sporadically all throughout it. If we do not see any flat surfaces where it breaks cleanly along, we call that fracture. If I were to smash this, it would break into a bunch of random looking pieces. Cleavage, on the other hand, is going to be when a mineral has these flat sides that it breaks along. So, for example, I can pinch flat sides here and here. I can also rotate it and find another pair of sides. Each of these pairs of sides are part of the same cleavage plane. So this is one cleavage plane, this is another, but if I look at this side, I'm not getting a nice flat end. Same with the other side here. So this sample that I'm looking at has two planes of cleavage, and if I look at it head on, you can see that they meet basically at a right angle. That's going to be our other aspect of cleavage we care about. So we want to know how many cleavage planes and at what angle. Sometimes cleavage planes are quite easy to figure out. So for example, this biotype mica, it is very, very flat. On the other sides, it does not actually have much flatness to it. And I can catch the light as I move it back and forth. It catches all at once. That's telling me that this is probably a cleavage plane. What's nice about micas is they tend to break nicely along these flat lines. So I can get little bits of glitter off if I pick at it. As you can see, I'm getting more flat sheets. Each of the pieces I break off of this should look like the same thing I had to start with. You will do a cleavage activity to begin with for your 101 lab, and then you'll also look at a set of minerals to identify the individual cleavages. Cleavages can go from having no cleavage planes, so that's going to be fracture, to having one cleavage plane, which is going to be like our mica, and then anything above that, from 2 planes to 6 planes, is going to also include some amount of angle. So this one, they had 2 planes meeting at right angles. You might have something like this where it forms more of parallelograms. Those are not right angles. So we have 90 degrees and not 90 degrees. That's going to be us looking at cleavage. Once we go beyond cleavage, we're going to start getting into our actually destructive methods. Our first destructive method is one of my favorites. It is the streak test. You have 2 different kinds of streak plates. You have a light colored one and a black colored one. So this streak plate on the left is really good for showing a streak for most minerals that are going to be darker in color. This one is what you're going to want to use for a light colored mineral, but I almost always start with the light colored one just because it's what I'm used to. So I will take a mineral, and you are going to apply some amount of pressure as you rub into it, and it should pulverize that mineral. So three different things could happen. You can either see a trail left behind like this. If you see that trail, you want to identify what the color is. So for me, this is a very, very dark metallic gray. You could have something happen like this where I'm going to do the same thing. You can hear there's quite a lot of effort put into that, and I don't see anything. That's when I want to move on to the dark one and do the same thing. I see that I have a white streak left behind. I could also end up with a sample that I try really hard on here. I don't see anything. I move over here and I get at most like a light trail or even no trail. That's going to have to do with the hardness of our mineral, which is our next test we do. So the reason we start with the streak test is it is our first measure of hardness. If a mineral has a hardness of 6.5 or less, it should leave a streak. If a mineral is harder than a 6.5, it will resist scratching more than the streak plates will, so it will not leave a powder behind. If you get a streak plate that happens to have a lot of powder and you're not sure, you should make sure to wipe it off with a wet rag, and that will allow you to see a nice clean surface. So, Right now we have streaks on these. Our next step then is going to be moving one step down, which is going to be looking at a glass pane. Glass has a hardness of about 5.5. So if I use a material that I know is softer than glass, I'm going to do the same thing as I did before. I'm going to apply quite a bit of force. You can see the mineral is powdering on this. I'm not getting any scratches inside of the glass though. So that tells me that this mineral is softer than the glass. The glass resisted the scratching. If I have something harder than the glass, I can start putting some pressure in and I can actually see some light scratches because these are quite similar in hardness to one another. So that's how you use a glass plate. It should always be placed firmly against a flat surface. You should hold it in place and then apply your force. After that, if you are going one step below that, you are going to use an iron nail. This has a slightly lower hardness than glass. The way you do this is very, very similar. You put the sample down, but you are going to rub that nail back and forth into that sample, making sure that you are applying a little bit of force, but not too much. You don't want to have the nail slip and then it stabs into your hand or anything. So you're doing just a light scratching with it. I tend to not utilize the nail very often. So far, this mineral we have looked at has left a streak, so it has a hardness less than 6.5. It did not scratch glass, so it has a hardness less than 5.5. Our next tool is going to be a copper penny. We're going to hold our sample and then dig into our sample with that penny. And I can see that it is cutting into that. If I'm not sure, I can even tip it to the side and tap it, and you can see it left quite a bit of that powder. So that means the penny is harder. Copper pennies have a hardness of 3. So that means we are getting into our lowest numbers of our hardness scale. Our only remaining tool is our fingernails. Now, I hate using fingernails for this. Your fingernail might have a different hardness than other people, depending on things like diet. Your genetics might impact that a little bit. If you get your nails done a lot, you might have either acrylic nails, which will have a different hardness, or if you remove those with acetone, that can weaken your nail as well. But the way you do it is you take your fingernail and you just dig into it, kind of like with the penny, but just side to side. And you can see I am generating some dust over here on this side. That means that my fingernail is harder than this. Fingernails tend to have a hardness of about 2 to 2.5. So that means that my sample I have here has a hardness roughly about 2 or less. That's how you end up doing a hardness test. That's really all there is to that. So we have looked at our 2 biggest things for our destructive methods now. Our remaining tests that we want to look at are going to be what are called other tests, other diagnostic tests, special tests. Sometimes they're called confirmation tests. There's a lot of different words for them. However, what they all have in common is they are going to be the last things you use on a mineral. So let's go ahead and start with one of the most common ones, which is going to be hydrochloric acid. Hydrochloric acid is not going to be something you should fear in this course, but you should keep an eye out for it. So some minerals, specifically carbonate minerals like calcite here, will actually react with acid. And I'm going to zoom in quite a bit on this. So here's my sample of calcite. I'm going to put a little bit of acid over here so you can see what it looks like just on a surface. It doesn't do much. If I put it on the calcite though, you can see that it is actually bubbling up on that calcite. The acid in here is reacting with the carbonate and creating carbon dioxide. This is very similar to what you would see if you were to put vinegar on baking soda. They are very similar reactions. Here's a different mineral that some people might confuse with calcite that has coloration. If I put a little bit of hydrochloric acid on there, You can again see not much is happening at that level. Sometimes you'll have something like a fossil. Fossils contain a lot of calcite typically, so if I put some on here, you can again see a lot of fizzing. It's in fact easier on that because it's an opaque surface, so you can see those bubbles rise up. So that's really how you use hydrochloric acid. Now, I will warn you, you should never put hydrochloric acid on something that is metallic. The reason for this is because most of our metallic minerals we look at are sulfide minerals. They will react with hydrochloric acid and create hydrogen sulfide gas, which is what gives rotten eggs its scent. That gas, not only is it not great for you, is very, very pungent and will make the entire building smell like rotten eggs. So please do not do that. You can't see it because I have my paper towel off to the side, but I am drying that acid off of each of these samples. And now I will make sure I wipe down that place on my station. That's all you have to do for hydrochloric acid. Our next test is going to be a fan favorite, and it's kind of an easy test in my opinion, because it's pretty easy to see the results. You are going to test for magnetism. Now, you will have a magnet placed inside of a bag. You should leave it in that bag. The reason it's in there is so that if a piece of a magnetic mineral breaks off, it does not get permanently stuck to the magnet. So here's my iron nail. In case you're wondering what we're doing, we should be able to pick up the magnet with our samples. The reason we do it that way, so here's a magnetic mineral. I'm going to plop it on and I can pick it up. That tells me this is magnetic. Some people will instead take a sample and then put the magnet on top. Well, if you have a flat enough sample, that magnet's going to sit there no matter what. This works really well for metallic minerals because those tend to be the ones you would expect to be magnetic. This one does not pick it up. It is non-magnetic. Our final mineral ID technique is kind of hard to see in lit up rooms. So I have to unfortunately turn off the lights briefly. And we are going to look at fluorescence. Now, this is a property quite a few minerals have, but it does not always happen for each sample of a mineral. The reason fluorescence typically occurs is you have some kind of contaminant inside of whatever your mineral is. So for example, this is a sample of atomite I have here. I'll turn on the light so you can see what it looks like. It has a slight yellow coloration to it. Around it, it has a lot of this reddish iron material. Now, under white light, it looks beautiful, but if you have an ultraviolet light or a black light and you shine it on it, it tends to glow slightly green. Now, we are using relatively weak ultraviolet lights. That way you don't need any personal protective equipment for this, but you can see that green in there. That green is due to traces of uranium. So I can move that off to the side and compare it with some uranium glass, which will glow quite bright because this is a purified version of that. So these are glowing off the same thing. Another thing that will tend to glow is going to be things like fluorite, like what we looked at earlier, but the issue is it glows a blue color just like your black light will be. So it's really hard to see that unless you have a nice high quality black light with quite a few filters. We may or may not have a few of those that you can utilize. So if you want to see what that looks like, ask your IA and they may be able to let you know.